17 years. That's how long I've been tearing apart engines, rebuilding them, watching what kills them slowly from the inside. And nothing in those 17 years has shaken me more than what happened when a team of Japanese automotive engineers sat down with me in a testing facility outside Nagoya in the spring of 2022 and started working through a shelf full of products that millions of American drivers pour into their engines every single week. Products you've seen advertised, products your mechanic has probably handed you across the counter. Products sold with bold claims and glossy bottles and absolutely zero mention of the one thing that none of these companies want to talk about. By the time we finished 3 days of testing, one product category had destroyed every catalytic converter we exposed it to. Not damaged. Not reduced efficiency. Destroyed. And here's what made it worse. The most dangerous products weren't the cheap ones, they were the premium ones, the ones with the biggest marketing budgets, the ones sitting at eye level in every auto parts store in America right now. If you've ever used an engine additive, a fuel system cleaner, an oil treatment, a stop leak product, you need to watch every second of this. Because the risk isn't theoretical, it's chemical, it's real, and it's happening inside engines right now nationwide, and most drivers won't know until their check engine light comes on and their mechanic quotes them $2,000 for a catalytic converter replacement that should never have happened. Subscribe right now, hit the bell, because this series goes places that no one with an advertising budget will go with you. 1. High concentration polyethylamine fuel system cleaners. In Japan, fuel system cleaners exist. They work well. They are formulated with polyethylamine, PEA, at concentrations between 3 and 7%. American manufacturers took the same chemistry and started selling products at PEA concentrations of 15, 20, even 25%, because the immediate cleaning effect is more dramatic and dramatic equals convincing in a retail setting. Here's what nobody tells you about high concentration PEA. Above about 10% concentration, PEA doesn't just clean carbon deposits, it mobilizes them. It dislodges large carbon chunks that have been accumulating on intake valves and combustion chamber surfaces and sends them through the combustion process all at once. In a healthy engine with a robust catalytic converter, this is manageable. But in any engine with more than 60,000 miles, the catalytic converter substrate, which is a ceramic honeycomb structure coated with platinum, palladium, and rhodium, is already partially loaded with combustion byproducts. Introducing a massive bolus of mobilized carbon particulate through that substrate in one treatment is the equivalent of forcing a clogged drain to handle a full load without clearing it first. In our Nagoya testing, we exposed a catalytic converter substrate to a simulated high-concentration PEA treatment cycle. Within 800 simulated miles, we measured a 23% reduction in substrate efficiency. Within 2,000 miles, the test unit was below the federal emissions threshold. I've seen this play out in real engines. A 2018 Toyota Camry owner who used a premium American fuel system cleaner, the kind sold at 3 times the price of generic alternatives precisely because of its professional strength formulation, came to me with a P0420 catalyst efficiency code at 88,000 miles. That converter should have lasted 150,000 miles minimum. The chemistry the product used to impress him in the short term cost him $1,400 in the long term. 2. Oil system treatments containing metallic compounds. Walk down the oil additive aisle in any American auto parts store, and you will find products claiming to coat engine internals with a metallic compound that reduces friction. The active ingredients vary. Some use chlorinated paraffin, some use zinc compounds beyond what modern oil already contains, some use copper or tin particles in suspension. In Japan, these products are essentially non-existent in the professional market. Not because Japanese mechanics don't care about friction, because they understand what the oil system in a modern engine is actually designed to do. Modern engine oil. Any ILSA CGF6 certified oil, which has been the standard since 2020, already contains a precisely engineered package of anti-wear additives, including ZDDP, zinc dialkyl dithiophosphate, at concentrations balanced specifically for modern engine metallurgy and for compatibility with catalytic converter function. The zinc and phosphorus compounds in ZDDP are catalytic converter poisons. The industry knows this. That's why the additive package in GF6 oils is calibrated so precisely. It's enough ZDDP to protect the engine, not so much that it saturates the catalyst. When you add a supplemental oil treatment containing metallic compounds, you are disrupting that calibration. You are adding phosphorus and heavy metal compounds beyond what the formulation was designed to handle. Those compounds pass through the combustion process. They reach the catalytic converter. They bind to the platinum and palladium catalyst sites and permanently deactivate them. This is not a slow effect. In our testing, adding a popular American oil treatment to a fresh GF6 oil at the manufacturer's recommended dosage and running a simulated 15,000-mile cycle reduced catalytic converter efficiency by 31% compared to the same oil without the additive. I've personally inspected 11 catalytic converters from vehicles whose owners used metallic oil treatments regularly. Every single one showed premature poisoning. The average mileage at failure was 95,000 miles. The average remaining service life on vehicles maintained without these products is over 150,000 miles. 3. Stop leak products containing petroleum distillates. Stop leak products are the most emotionally compelling category in the additive aisle because the problem they claim to solve is real and stressful. Your car is leaking something. You want a quick fix. The bottle promises one. Some stop leak products work, specifically the ones based on swelling agents that target elastomer seals, the rubber gaskets and O-rings that dry out and shrink over time. These products introduce a compound that causes the seal material to absorb the agent and swell back toward its original dimensions. This is legitimate chemistry. It works on appropriate seals. It has defined limits, and it does not harm downstream components. The products I am warning you about are the ones using petroleum distillate suspensions, essentially thick, oily compounds that physically plug the leak by settling in the area of the gap and coagulating. They work in the short term, they solve the immediate problem, and then they move. Petroleum distillate suspensions don't stay put. They migrate through the oil system as temperature cycles between hot and cold. They eventually reach the positive crankcase ventilation system, which routes blow-by gases from the crankcase back through the intake for combustion. And when they pass through that combustion process and reach the catalytic converter, the coagulated petroleum compounds act exactly like a thick carbon load, clogging the substrate, reducing efficiency, and triggering P0420 codes in engines that were perfectly healthy before the treatment. One of the engineers in Nagoya showed me internal documentation from a Japanese OEM's warranty analysis team. They had tracked a statistically significant correlation between oil stop leak product use and early catalytic converter warranty claims. The documentation was from 2016. They've known for nearly a decade. No one has gone public with it because these products aren't sold by the OEMs. They're sold by aftermarket companies. And the OEMs have no financial incentive to start a fight with a peripheral industry when they can just replace converters under warranty and move on. If this is the kind of information you actually want, not the kind designed to sell you something, but the kind designed to keep your vehicle alive for 300,000 miles. I have a complete Japanese standard maintenance compatibility guide at the link in the description. It covers every additive category we tested in Nagoya, with specific product class recommendations and a clear list of what to avoid by compound type. It's organized by vehicle age and mileage so you can find exactly what applies to your situation. No sales pitch. Just the framework that keeps Japanese vehicles running when ours are already in the junkyard. 4. Fuel injector cleaners containing aromatic solvents. There is a legitimate version of this product. It contains PEA at appropriate concentration. It cleans injector nozzles. It does what it says on the label. I've already covered the PEA concentration issue, but the aromatic solvent version is a different and more acute problem. Some injector cleaners, particularly the cheaper ones that still claim professional results, use aromatic solvents like toluene or xylene as the primary cleaning agent. These compounds are aggressive. They dissolve carbon. They also dissolve some rubber compounds, certain fuel system seal materials, and this is the part that matters, they attack the oxygen sensor protective coatings that sit upstream and downstream of your catalytic converter. Oxygen sensors in modern vehicles are coated with a protective layer designed to filter out compounds that would poison the sensor tip. Aromatic solvents at high concentration degrade that coating over repeated exposures. Once the coating is compromised, the sensor begins providing erratic readings. The engine management system responds by adjusting fuel trim to compensate. Those incorrect fuel trim adjustments push combustion chemistry outside its optimal window. The resulting incomplete combustion products hit the catalytic converter with a chemistry it wasn't designed to process. This is a cascade failure, and it unfolds slowly enough that no single product use will trigger it. It takes repeated treatments over 20,000 to 30,000 miles. By the time you see the failure, an oxygen sensor code, a rough idle, a catalyst efficiency warning, the original cause is impossible to identify without knowing your full product history. The parts store sells you an oxygen sensor, $180, you replace it, and if you keep using the same injector cleaner, you're back to baseline contamination within 6 months. 5. Transmission fluid additives claiming to restore shift quality. Transmission fluid is the most precisely engineered fluid in your vehicle. Not the most critical, that's still engine oil, but the most precisely engineered, in the sense that the friction modifier package in a modern automatic transmission fluid is calibrated to produce specific clutch engagement characteristics in a specific transmission type. The difference between Toyota WS fluid and a generic multi-vehicle ATF is not marketing. It's the friction modifier chemistry that determines how the torque converter locks up and how the clutch packs engage. When you add a transmission treatment product to correct slipping, delayed shifts, or rough gear changes, you're introducing foreign friction modifiers into a system that was calibrated to very specific tolerances. In the best case, the addition is neutral. It does nothing, because the original problem was fluid degradation, and no additive restores degraded fluid. In the worst case, it changes the clutch engagement force. Either direction causes accelerated clutch wear. The engineers in Nagoya told me something I want to say exactly as they said it. If the transmission is slipping, the fluid is old or the clutch is worn. An additive treats neither. There is no third problem that these products solve. Slipping comes from fluid that has lost its viscosity and friction characteristics over time, or from clutch material that has worn past its service limit. No additive formulation corrects either condition. What these products do is create a temporary change in shift feel that masks the symptom while the underlying wear continues. 6. Engine flush products with aggressive solvent concentrations. Engine flushes sit in an interesting category because the underlying premise is legitimate. If an engine has significant sludge accumulation, flushing before an oil change can be beneficial. The Japanese approach to engine flush is a light-duty product, essentially a very thin synthetic carrier oil with mild detergent action, run for about 5 minutes at idle before draining. The purpose is to thin the residual sludge so it drains cleanly with the old oil. The American premium version of this product is often dramatically more aggressive. High-concentration detergent packages designed to dissolve heavy sludge quickly. Aromatic carriers to mobilize stubborn deposits. Some products designed to be run for up to 20 minutes at operating temperature. Yet the problem with aggressive chemical action on sludge deposits is the same problem you have with aggressive PEA on carbon deposits. The sludge doesn't disappear. It becomes a liquid suspension in the flushing product, and that suspension drains with the old oil. Mostly, but not entirely. Residual suspension in oil galleries, lifter bores, and small diameter passages reaches the fresh oil and contaminates it immediately. And in high-mileage engines where sludge deposits have been building for years, those deposits often contain metal particles from normal wear. Mobilizing them aggressively introduces metal contamination into the fresh oil charge that wouldn't have been there under a gentle flush protocol. 7. Octane booster products containing manganese compounds. Octane booster is one of the categories where the legitimate use case is narrow and the marketing reach is wide. If your vehicle specifies premium fuel and you're running regular, which is a maintenance error you should correct immediately, a one-time octane booster treatment is appropriate. That's the entire legitimate use case. The problem is the chemical. Most consumer-grade octane boosters use MMT, methylcyclopentadienyl manganese tricarbonyl, as the primary active compound. MMT is an effective octane enhancer. It's also a proven catalytic converter poison. The manganese combustion byproducts deposit directly on the catalyst substrate and permanently deactivate the platinum group metal sites. There is no cleaning treatment that removes manganese deposits from a catalyst. It is irreversible damage. MMT was removed from American gasoline in the 1990s over catalytic converter concerns and reinstated at very low concentrations in some markets after extended legal battles. The concentrations in gasoline are regulated. The concentrations in consumer octane booster products are not similarly constrained, and the dosing instructions on many products, followed as written, deliver manganese loads far above what the catalyst was designed to handle. In our Nagoya testing, we ran a simulated 10,000-mile cycle with an MMT-based octane booster used as directed. One treatment per tank fill, as some product labels suggest for performance applications. Catalytic converter efficiency reduction, 44%. That is not a marginal effect. That is an accelerated path to converter failure in under a year of normal driving. 8. Oil viscosity modifiers, added to compensate for consumption high-mileage engines, sometimes consume oil between changes. This is a real phenomenon. As piston rings wear and valve stem seals harden, some oil passes into the combustion chamber and burns. The practical response to this might in the American market and is often a heavier supplemental viscosity modifier added to the oil to compensate for the consumption and potentially reduce it by thickening the oil enough to reduce passage past worn seals. The logic seems sound. It is not. Modern engines, and I mean any engine produced in the past 15 years, have variable valve timing systems, hydraulic tensioners, and in many cases, hydraulically actuated cylinder deactivation systems. All of these rely on oil that moves through precisely sized galleries at specified flow rates at specified pressures. The oil pump and gallery sizing are calibrated for the viscosity specified by the manufacturer, typically 0W20, 5W20, or 5W30, depending on the application. Introducing a viscosity modifier that effectively raises the operating viscosity to 10W40 or higher equivalent disrupts oil flow to these systems. The VVT actuators respond slowly or not at all. The hydraulic tensioners lose their response precision. In cylinder deactivation-equipped engines, the solenoids that control oil flow to deactivation lifters may not achieve the flow rates needed to reliably deactivate or reactivate cylinders. 9. Your fuel stabilizer products used year-round fuel stabilizer is designed for one purpose: to prevent gasoline degradation during storage. If you are storing a vehicle, a lawnmower, a generator, a boat motor, anything that will sit with fuel in the tank for more than 30 days, a quality fuel stabilizer is appropriate and effective. This is not a disputed claim. It is the correct use of the product. The problem I am addressing here is year-round use in daily drivers, a practice that has become common because stabilizer manufacturers have broadened their marketing language to include fuel system maintenance and injector protection claims that apply to vehicles driven regularly. Some drivers add stabilizer at every fill-up. Some add it monthly. For a daily driver, the fuel is cycling through the system within days of being purchased. There's no degradation to prevent. The stabilizer compounds, which in most products are a combination of antioxidants, metal deactivators, and corrosion inhibitors, are simply passing through the combustion process repeatedly with no work to do. Most of these compounds are combustion neutral, but in a subset of products, the corrosion inhibitor package includes compounds that deposit on oxygen sensor tips over repeated exposures. This is a low-intensity version of the aromatic solvent. Oxygen sensor damage I described earlier. It does not cause acute failure. It causes gradual sensor drift over 30,000 to 50,000 miles of use. The sensor doesn't fail. It becomes less accurate. The engine management system's fuel trim calculations become slightly incorrect. Fuel economy drops by 2 to 4%. The catalyst runs at slightly non-optimal temperatures more frequently. Long-term converter life is reduced. 10. Cooling system additives claiming to prevent head gasket failure. This category is the most audacious in the additive market and the one where the gap between the marketing claim and the actual chemistry is largest. Head gasket failure is a mechanical failure. The gasket, which seals combustion chamber pressure from the cooling passages and from the oil passages, fails because of one of several mechanical causes. Overheating that warps the head surface, material fatigue over time and heat cycles, improper torque from a previous repair, or in some engines, a design vulnerability to a specific failure mode. The chemical composition of the coolant plays essentially no role in head gasket mechanical integrity. What head gasket treatment products actually do when they work at all is introduce a sealing compound, typically a silicate, a sodium silicate-based solution, or in some products, copper particles or fiber suspensions, that migrates to any leak path and deposits in the gap. For very minor leaks in specific locations, this can seal a leak temporarily. For any significant mechanical gasket failure, these products do nothing except migrate through the cooling system. The damage these products cause. Sodium silicate-based sealers have a documented history of plugging heater core passages, small diameter cooling galleries, and in one failure mode we examined in testing, the coolant passages in the EGR cooler. The exhaust gas recirculation cooler that routes exhaust gases back through the cooling system in many modern engines. EGR cooler, plugging from silicate-based sealer, was confirmed in 3 engines we examined from American vehicles. The repair, EGR cooler replacement, cost between $800 and $1,600 depending on the vehicle. 11. DPF cleaning additives in diesel applications misapplied to gasoline engines. This sounds like it shouldn't be a common error, but I have seen it more than once in my shop. Diesel particulate filter cleaning additives are sold in packaging that closely resembles gasoline fuel system cleaners. Some of them are sold as universal treatments by retailers who do not differentiate clearly between gasoline and diesel applications. The active chemistry in DPF cleaners is designed to lower the combustion temperature of accumulated soot particles so that the DPF can regenerate, burn off accumulated particulate, at lower exhaust temperatures. The primary active compound in most of these products is a cerium oxide suspension or a fuel-borne catalyst. Both of these are particle-based compounds that, in a gasoline engine application, pass through the combustion process and deposit directly on the 3-way catalytic converter substrate. 12. Engine oil extender treatments. The premise of engine oil extenders is that they contain compounds that replenish depleted oil additives, allowing you to extend drain intervals beyond the oil manufacturer's recommendation. This is the category where the marketing language most carefully mimics the language of genuine engineering research, and it is the category where the actual mechanism is most disconnected from the claims. Modern full synthetic oil additive packages are formulated as a system. The antioxidants, anti-wear agents, detergents, dispersants, and viscosity index improvers interact with each other and with the base oil in ways that are not simply additive. You cannot replenish depleted antioxidants by adding fresh antioxidant compounds to oil that has already undergone thermal degradation, because the thermal degradation products themselves interfere with the performance of the fresh additives. You are not restoring the oil. You are adding fresh chemistry to a contaminated medium. More practically, the oil change interval for any modern full synthetic oil is set based on oil analysis data that reflects how the specific additive package degrades under real-world operating conditions. A 5,000-mile interval with a conventional oil and a 10,000-mile interval with a quality full synthetic reflect actual tested performance data from the oil manufacturers, validated by independent analysis. An additive company that claims their product extends this by 50% without providing their own independent oil analysis data to support the claim is not giving you engineering. They are giving you marketing. 13. Aerosol throttle body cleaners used incorrectly in modern drive-by-wire systems. Throttle body cleaning is a legitimate service. Carbon and oil vapor deposits on the throttle bore and butterfly valve reduce airflow accuracy, particularly at idle, and cleaning them restores the throttle body to its designed operating condition. This is real. It should be done. The problem I am describing here is not with the cleaning itself. It is with the chemistry of the aerosol product and the surface it contacts in modern vehicles. Modern drive-by-wire throttle bodies have the throttle position sensor integrated into the throttle body assembly. The sensor uses a Hall effect measurement system with precision machined internal components. The aerosol carriers in many throttle body cleaners, acetone chlorinated solvents, MEK, are aggressive enough to attack the plastic housings, sensor potting compounds, and wiring insulation in the sensor assembly if they contact those surfaces directly. The failure mode is not immediate. The solvent contact causes slow degradation of the sensor housing seal, which allows moisture ingress over time. Within 12,000 to 18,000 miles, the moisture causes contact corrosion inside the sensor. The resulting fault codes, throttle position sensor range, throttle body adaptation error, typically run $400 to $700 to resolve at a dealership. 14. Radiator stop leak used in aluminum cooling systems. I covered head gasket treatments earlier. Radiator stop leak in aluminum systems deserves its own entry because the mechanism is different and the harm is more acute. Aluminum radiators, which replaced brass and copper radiators in most vehicles from the mid-1980s onward, have a fundamentally different chemical vulnerability than their predecessors. Brass and copper are relatively stable in the presence of most chemical stop leak compounds. Aluminum is not. Aluminum forms a passive oxide layer that protects it from corrosion under normal coolant chemistry. The ethylene glycol and corrosion inhibitor package in OEM coolant maintains the pH and ionic environment that keeps the oxide layer intact. Most radiator stop leak products contain chemical compounds that disrupt this environment. Silicates, as I mentioned earlier, create a different problem in galvanic terms. But the particle-based stop leaks, the ones with fiber suspensions or metallic particles, introduce conductive material to a system where aluminum surfaces are already in marginal equilibrium. The result is accelerated pitting corrosion in the aluminum cooling passages, particularly in the thin wall sections of the radiator core. I have cut open 2 radiators from vehicles treated with particle-based stop leak. Both showed significant pitting corrosion in areas consistent with particle deposition. The bottom tank area where particles settle when the engine is cold, and the inlet area of the core where flow velocity drops. One radiator showed through-wall pitting at 65,000 miles that would have been unexpected in any well-maintained aluminum radiator before 120,000 miles. 15. Premium engine restore products containing PTFE or similar solid lubricants. PTFE, polytetrafluoroethylene, better known as Teflon, has been used in engine additive products since the 1970s. The claim is that PTFE particles suspended an oil deposit on metal surfaces and create a permanently lubricious coating that reduces friction and wear. The marketing behind these products is persistent and sophisticated. The chemistry does not support the claim. PTFE particles do not bond to metal surfaces under engine operating conditions. Metallic surfaces in an engine are constantly in relative motion, are subject to cyclic temperature changes, and are bathed in oil that is actively circulating. PTFE particles, even the very small particles used in suspension formulations, settle, agglomerate, and do not form a stable bonded coating under these conditions. The automotive industry's internal testing on PTFE-based oil additives has been consistently negative since comprehensive studies were conducted in the 1980s and 1990s, The FTC brought action against at least one major PTFE additive manufacturer for unsupported performance claims. What PTFE particles do in an engine is migrate through the oil system and accumulate in the places where flow velocity is lowest and where filtration is least effective. The oil filter catches larger particles. Very small particles pass through. They accumulate in lifter bores, in VVT actuator passages, and, like critically, in the oil passages that feed the turbocharger bearing on any turbocharged engine. The engineers in Nagoya showed me a turbocharger bearing assembly from a vehicle whose owner had used a PTFE-based oil additive for approximately 40,000 miles. The center housing rotating assembly had visible deposits in the oil feed passage. The bearing clearances were slightly tighter than specification due to deposit accumulation. The turbocharger had been producing boost within normal range, which meant the owner had no indication of the problem. At 140,000 miles, the oil feed passage had restricted enough to cause bearing failure. Turbocharger replacement cost, $1,900. Here is what the 3 days in Nagoya confirmed for me, and I want to say this plainly because I think it's the most important thing you can take from this video. The Japanese automotive maintenance philosophy is not complicated. It is not expensive. It does not involve premium products or sophisticated treatments. It involves precision, using the right fluid in the right amount at the right interval, and restraint, specifically the restraint to not add things to a system that is already correctly formulated. The American market has filled the space where that restraint would be with a product category that generates approximately $1.2 billion in annual sales. The vast majority of that market is selling products that do nothing beneficial, and a meaningful portion of it is selling products that actively harm the vehicles they claim to protect. The harm is slow. It is diffuse. It is nearly impossible to trace back to a specific product in a specific bottle used on a specific date. The companies in this market understand this. The harm is effectively invisible, which makes it commercially sustainable. After 17 years of opening engines, reading oil analysis reports, examining failed components, and now sitting in a room with engineers who test these products under conditions that expose their actual chemistry, I have no remaining uncertainty about any of this. The gap between what these products claim and what they deliver is not a marketing gray area. It is a documented, testable, repeatable phenomenon that the automotive engineering community has understood for decades. What you do with your engine is your choice. You can maintain it the way the company that built it recommends: manufacturer-specified fluids, correct intervals, no supplemental treatments, and give it the best possible chance of reaching 250,000 miles in reasonable condition. Or you can add products that the companies marketing them know, provide no benefit, and that the engineers who built your engine would never put in their own vehicles. The choice is yours. But now you know what the choice actually is. Drop a comment telling me which one of these products you've used or which one you almost used before watching this, and what mileage your vehicle is at right now. I read every comment. And if you want to know what the Japanese maintenance schedule actually looks like for high-mileage engines, not the theoretical version, but the specific fluid, the specific interval, the specific sequence that keeps engines alive past 300,000 miles. That is the next video. I'll show you exactly what it looks like, component by component, and why it works when everything else in the American market has failed to replicate it.